Now let's move on to some platform-specific issues we encountered on iOS. The kind of problems that are not obvious and frankly a bit strange at first. 1. Black screen caused by RenderTexture format. In one project, the minigame launched on iOS and immediately displayed a black screen. The error log indicated RenderTexture format not supported. After investigating, we found that the project was creating a 32-bit HDR render texture using the R11G11B10 format. URP, in some configurations, defaults to creating HDR render textures. In this case, the team implemented resolution scaling by rendering 3D content into a custom render texture, and that render texture was also using R11G11B10. Here's where it got interesting. On their iPhone 12, the game black screened immediately. On our company's iPhone 12, same model, it worked perfectly. So we went on site, reviewed their code, and ran a simple experiment. We forced the render texture format to ARGB32. The result? No more black screen on their device. That led us to suspect that the issue might be related to the lack of an alpha channel in R11G11B10. So we implemented a compatibility check. If the device does not support R11G11B10, fall back to a format with an alpha channel. Later, we discovered that their iPhone 12 was running a somewhat unusual iOS version. That explained why the issue reproduced only on specific devices. However, changing to ARGB32 introduced another problem. The visual output changed. For example, a building upgrade effect that was supposed to appear golden and HDR rich became flat and slightly washed out because HDR information was lost. So we tried switching to 64-bit HDR. That restored the color accuracy but increased bandwidth and GPU pressure. In the end, the team adopted a balanced strategy. Use non-HDR formats for medium and low-quality settings. Use 64-bit HDR only on high-end devices that support it. Otherwise, gracefully fall back to ARGB32. The key takeaway here is add runtime format compatibility checks and design a tiered fallback strategy that balances visual quality and performance. 2. Hair flickering on iOS, depth precision issue. In another project, we ran into a classic but subtle rendering issue on iOS, hair flickering. On desktop and other platforms, the hair rendered correctly, but on iOS minigames, it visibly flickered. Our first instinct was Z-fighting. After reviewing the shader, we found that the hair material used 2 rendering passes. The fix turned out to be surprisingly simple. In the second pass, we added offset 9:1. What does this do? It slightly biases the calculated depth value toward the camera. In theory, both passes should produce identical depth values, and depth testing, usually less equal, should pass consistently. However, due to lower depth precision in the iOS minigame environment, small floating point differences caused instability. One frame, depth is slightly larger. Next frame, depth is slightly smaller. As a result, depth testing would pass one frame and fail the next, causing flickering. By applying offset 9:1, we ensured that the second pass always renders slightly closer to the camera. That tiny bias stabilizes depth comparison and eliminates the flicker entirely. After the change, the visual result matched the expected stable output. If you encounter similar flickering issues, especially on iOS minigame platforms, consider depth precision as a potential root cause. Sometimes the problem isn't logic. It's floating point precision differences across platforms, and a small depth bias can make all the difference.